Hi guys, today we will learn about the common emitter configuration of BJT amplifier. We did cover this a little bit in the application of BJT, but I just want to go deeper into um, this topic. But first of all, I have a couple notes I need to mention, so let's get to this.
So before we start, I want to mention that if you go to the course module and under the Amplifier module, you can see I put on an extra note called extra note of H parameter and expanded model. So you can click on this note. So in this note, you can file two topics. The first thing is a part of the note that was prepared by Dr. Peter Cassell. He prepared this note for the lab on H parameter. So if you found any confusion regarding my note on H parameter, you can look toward this. He used a more detailed approach and he put a lot more equation in here. So hopefully this can help you derive all of the equation you need for the lab. Second of all, at the end of the note, we have an extra portion for the lab that you may need, which is the expanded hybrid pi model. So remember that I say in the last lecture, I showed you two versions of the circuit. One is basically the equivalent model with the transconductance parameter, and second is the beta, which is the amplification factor. So this note will explain and give all of the equivalent equation. So if you run into this lab, you can open this note out for to have the correct equation for your lab. We will go through the common emitter amplifier configuration. So we can have a common emitter configuration here. Why is common emitter? Because the emitter port of the transistor is grounded, so you can call it common emitter. Okay, this circuit, you saw that before, is basically a voltage divider biasing circuit with coupling capacitor. So why you need a coupling capacitor? So this coupling capacitor CC is coupled directly into the base of the BJT to provide DC isolation between the amplifier circuit and the signal source. So imagine if you replace BS with a DC circuit, then you know that from here to here it will be open circuit. But if you replace VS with a AC signal, then now you can run this. Now you can have this circuit acting as a amplifier. Another thing is regarding like voltage divider biasing. So the biasing is the DC. Okay, as a DC biasing is established by R1 and R2, and because DC biasing is this DC biasing will not be disturbed from the source, because in DC condition this knot right here is an open circuit. As I mentioned, the coupling capacitor here is to isolate the DC component of the source to the base, right? You don't want to amplify the DC component, you just want to amplify the AC component of the source. So what happened to the AC component? What happened to this coupling capacitor in AC? So you can write the magnitude of this capacitor so basically in AC, this capacitor acting as an impedance, right? So it's kind of like a resistance, but for AC condition. So you can calculate easily the magnitude of this capacitor impedance which is 1 over 2 pi f cc. Okay, and cc is the capacitance, the capacitance of this capacitor. Why is it magnitude? Because impedance is it has two components. It has a real and imaginary component. So you actually want to calculate the magnitude of the impedance. So next is you can see next is I want to mention that F stands for the frequency of the AC component in your source. Okay, so let's do some thought experiment. Let's assume that CC is equal to 10 microfarad. Let's calculate this the impedance of our capacitor given frequency, the source frequency at 1 kilohertz, 1 megahertz, and 1 gigahertz. So here's our result. At 1 kilohertz, we have the impedance to be 15.9. At 1 megahertz, the impedance is 0.59, and at 1 kilohertz, the impedance is at 15.9. So we can effectively assume that in AC condition, especially if you have something over 1 or 2 kilohertz, this capacitance becomes short circuit. Okay, so therefore you can write the small signal equivalent as below, and you just like normally, and you can get rid of this coupling capacitor. So next we will try to analyze the voltage gain of this amplifier using this small signal equivalent circuit. One more thing to mention is that we also will try to figure out the input resistance value of this amplifier and the output resistance value. How can we define input and output resistance? Basically, as I discussed before, if you treat this as a two-port network, input resistance is the resistance that you see at the input port. So that means what is the resistance of, if you just measure the resistance at this two port right here, how like what is the value of the resistance you can measure if you just plug in and measure from here. And output resistance likewise is the resistance that you saw at the output port of your two-port network. So if it's an amplifier, you need to find the gain. Okay. So the first step, if you want to find the gains, you need to find the input, you find the output, then you calculate by you divide the output for the input, so output over input, you get the gains. So we have the expression for the output here, VO equal minus GM V pi multiplied by for the parallel of RO and RC, and that's because we have the current in here is basically the current going into this direction, so that's why you put a minus on. You have the current multiplied by the resistance, so you have to combine these two together, that's why you have the parallel sign, and basically it's just Ohm's law to calculate the output. For the input, it looks a little bit complicated, but it's actually same. So first let's start with V pi first. So you know you start with Ohm's law. Actually, sorry, you start with voltage divider rule. So you know that V pi is basically, you can apply V pi, you can calculate V pi by voltage divider rule with RS and this whole giant resistance right here. And this resistance basically is pretty simple. It's equal to R1 R2 R1 parallel R2, which is this one, parallel with this one. So you have R1 R2 in parallel, and you parallel one more with R pi. Okay, then you use voltage divider rule to figure out the relationship between V pi and Vs. Then you can calculate what is Vs. And finally, you get the signal gains. You divide, you do the division of VO over Vs. Then you have the expression for your voltage gain. What you want to do next is to add a resistor to your emitter. So now you have a resistor, emitter resistor right here. And some of you may ask, why should I add emitter resistor here? I would suggest you go back to the voltage divider biasing and bias stability lecture that I gave. I will link toward that in the description. And in that lecture, basically we know that if you add a resistor to the emitter, basically we can stabilize the Q point against different variation of amplification factor or beta. So likewise, if you apply this emitter resistor for your AC amplifier circuit, you can do the same thing. You can protect your voltage gain to be less dependent on your amplification factor beta. And one last thing I want to notice is even though the emitter of this transistor is not directly connected to the ground, this configuration is still preferred as common emitter amplifier. So let's find the gain for the circuit. So if I have the circuit with the emitter resistor in here, first I need to convert this whole circuit to the equivalent circuit, right? But how can we develop that? So easy, you can follow this step. So we start with the 3-terminal transistor. Okay, so from the 3-terminal, I want you guys to convert that to the 2-port model or the hybrid pi equivalent model. So from here to here. Next is you need to this is small, but it's actually the largest step, which is you need to sketch off the remaining things around this 3-terminal and connect it to here. So I would follow this recipe called back BEC. So go from the base to everything around the base, then the emitter, then the collector, so you don't forget anything. So you start with the thing that right next to the base is this 2 resistor right here, and instead of connecting all the way to VCC, you can just convert the equivalent, which is R1 parallel R2. Then you go to what is next, connecting to this circuit. This parallel resistor in here. Parallel resistor in here, which is first is the source resistance, then the source voltage. So you connect that together. Second, you move to E. So put in your emitter resistor in here, and finally connect your collector resistor, and you can have your equivalent circuit. So now let's really find the gain. So in order to find the gains, remember we have to find the expression for the output voltage, find the expression for the source voltage, divide the output for the source, then you have the gain. So first let's work on the output. So we first analyze this loop. We know that the output voltage equal to the output voltage we can use Ohms laws for current going through this collector resistor in here. So you can write your output voltage as negative beta IB multiplied by RC. So next, we want to find output, our input, which is the source voltage, but let's start with the input voltage at the base first. So in order to do that, we have to analyze this loop here. So if you use Kirchhoff voltage law around this loop, you can have the input, the Vin, equal to current going through, equal to the voltage across this resistor, so IB multiplied by R pi, then voltage across this resistor, which is emitter current, IE, multiplied by RE. And you know IE is equal to 1 plus beta IB, so that's another way you can get around. So finally, you can use voltage divider rule for this loop to figure out what is the expression for the source voltage Vs. But in order to do the voltage divider rule for this loop, you actually need to replace this entire branch of the circuit with a expression for input resistance Ri. So first, if you want to do that, first we need to derive the input resistance at base, which is basically so you can have Vin over IB, which is basically the voltage across these 2 points and the current going in, and that will be equal to R pi plus 1 plus beta RE. Okay, so basically you divided this whole expression for IB and you can have this. So second, you can derive the input resistance pretty easily, because if you can replace this whole branch with RIB, then you just have to make it parallel to this one, which is R1 parallel R2. So now you have your Ri equal R1 parallel R2 RIB. So last you can have your source. You can derive your source voltage using voltage divider rule. So you can have Vin, okay, this voltage here, equal to Ri over Ri plus Rs multiplied by Vs. Then you flip the terms over, you can have the expression for Rs equal Ri plus Rs over Ri multiplied by Vi. So finally we can get the gain. So the gain is basically Vo over Vs. So it's equal to, so what's our Vo over here? So you bring this term, put it down on the top. Okay, and what is Vs? Vs is here. So bring this term, put it on the bottom, then you can have the gain to be equal to negative beta RC Vin over
I think if
IB multiplied by 1 over Vs.
If K has
Or you can just plug everything together and write it as
but he kept saying
the gain
it's too much
equal to this whole piece right here. I'm not going to read it out for you.
because
So if you have your expression for the gains in here, okay, if you look at this expression, first of all, look at this term first.
I don't
Okay,
understand from
so usually you have the input resistance, which is the resistance for your entire system. you can represent for your entire
worried
system.
about
Then you have the source
somebody
resistance.
will
That
kill
means
me.
in your source there's you have wire and something. So there's
But
a
I'm curious
small
why does he
resistance
think
in
like
there.
this?
If this number is relatively smaller or a lot smaller than this number, what will happen? So ask yourself the question first.
No one can.
Okay, so basically if this RS is very small, technically this whole term will become 1, right? Because this one will go to 0, Ri over Ri become 1.
Even though
Okay.
we make a scene,
Another thing you
and
need
even
to
though
see
we got
is, so
punishment,
if you have 1 plus beta
we are
RB, which is
protect us.
this, so it's a lot larger than R pi, then you can get rid of this term, R pi, in your equation. Then you can have your equation to be this. Okay, then actually, above you have beta, under you have 1 plus beta. Usually, if you in practice you have beta around 100, 150, something like that. So 100 over 101 is technically not a huge factor. Okay, you can assume it to be 1. Then finally, you can have the gains to be equal to negative RC over RA. Okay, so this is a very convenient way to design the gain. So these two equations show that the voltage gain for this circuit is less dependent on the current gain beta, in that there is smaller change in voltage gain when the transistor current gain changes. So you, the circuit designer, now has more control in the design of the voltage gain. But this advantage also comes at the expense of a smaller gain. Time when the emitter resistor must be very large or large enough for the purpose of DC design, but degrades the small signal voltage gain too severely. We can use an emitter bypass capacitor. Okay, just this new capacitor over here. This one. So we can use that capacitor to effectively short out a portion of one of the emitter resistance as seen in the AC signal. So technically, in DC analysis or DC condition, this CE will become open circuit, and you can remain a very large emitter resistor here. However, in AC, you can short out this in this path. Then effectively, you only have RE1 remaining in your system. Therefore, you can see that this is why sometimes this is called emitter bypass capacitor, because you use this to bypass a large portion of your emitter resistor. So that's it for today. If you have time, please go through some examples in the textbook. For example, example 6.5 is pretty good to practice calculating the gain. And good to see how the emitter resistance, the voltage gain can be insensitive to the current gain. The example 6.6 is good practice on PNP scenario. And finally, I also want you to try out, or at least go through example 6.7 to exercise with the bypass capacitor that we discussed in the last slide. Next lecture, I will try to go through AC load line, so it will be similar to DC load line, but will be applicable for our AC analysis.
this is the end of our lecture video. Thank you very much for watching, and I will see you guys next time. Bye bye.